Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 13. Numerical Computation of Multiple Integrals. Multiple integrals appear in a variety of science and engineering fields and real-world applications, especially in situations where we need to integrate over a two-dimensional or higher-dimensional region. For example, calculating the mass, center of mass, and inertia moment of a two-dimensional planar object requires double integrals, and the double integrals are replaced with triple integrals if the object is considered to be three-dimensional. Two- and three-dimensional integrals are often encountered in electromagnetism, gravitational fields, heat transfer, fluid mechanics, structural analysis, geography and environmental sciences, economics, computer graphics and image processing, and so on. Numerical computation of multiple integrals typically involves methods for approximating the value of integrals when an analytic solution is difficult or impossible to obtain or the region of integration is too complicated. Analytical methods may work for simple cases, but for more complex functions or irregular regions, numerical integration becomes necessary. Even if the integrand is not that complex, some functions involve piecewise definitions, singularities, or rapidly oscillating behavior, making them difficult to handle analytically. In practice, most integration regions are described by more complicated boundaries, and it is hard to express the limits of integration in a manageable form, making it difficult to evaluate the integral analytically. Numerical approximation of double integrals is relatively easy when the integration domain is rectangular. Domain D is defined as x from A to B and y from C to D. To illustrate the integration of fxy over a rectangular domain, consider the following double integration, where fxy is assumed to be an integrable function and not equal to the product of uppercase x and uppercase y functions, because the case of equality reduces it to the product of two single integrals. Fubini's theorem states that the double integral of any continuous function fxy over a rectangular domain can be calculated as an iterated integral. In this regard, we set, which allows the double integral I to be written as follows. In generalizing the numerical integration procedure, we exploit the idea that all numerical methods can be expressed as a weighted sum, where n is the number of integration points, xi, wxi for I equals 1 through n is a set of abscisses and weights depending on the method used. Then, the double integral I can be expressed as follows, where m is the number of integration points and yj, wij for j equals 1 through m is, as before, a set of method-dependent abscisses and weights. Combining the two integrals, we obtain the following expression. Note that the summation representing the approximation of the integral over the y variable is inside the outer summation sign. The outer summation sign accumulates the inner sums, as illustrated with the pseudocode segment. Consider the double integration an irregular domain. For all rays drawn parallel to the y-axis, in the interval from A to B for the domain D, seen in the figure, the variation of the y variable ranges from the lower curve to the upper one. So we can describe the domain as follows. The integral is transformed to a numerical integration over a fixed integration interval. That is, the integral can then be approximated as follows. Where ui, vi are evaluated at xi, and tiwti's are the quadrature for integration over the t variable. Triple integrals are integrated in the same manner. For a domain of rectangular prism, we approximate the following integral as where n, m, and k are the number of panels or integration points for x, y, and z variables, wxi, wyj, and wzk are the weights corresponding to 11, yj, and zk integration points, respectively. Let us consider a planar region, described by the parabola y equals x squared over 2 and the line y equals x, as shown in the figure. The following double integral gives the polar inertia moment of the planar region. We wish to estimate the polar inertia moment using the two-point Gauss-Legendre quadrature for each integral. First, we want to convert an integral over the y variable with variable limits to one with constant limits, ranging from -1 to 1. This is to take advantage of the tabular quadrature in the original range without the need for further processing. We apply the following y substitution for the reasons. We refer to video 12. The substitution yields the following integral over the t variable. We then replace this integral with that of the one in the original double integral. We get the original double integral is now expressed with fixed limits, where we define the integrand f as a function of x and t. The integral of f over variable t is replaced with the Gaussian sum, where tj and wtj are Gauss-Legendre quadrature. The inertia moment is now expressed as the integral of gx from 0 to 2. Similarly, the integral of gx from 0 to 2 is also replaced with a Gaussian sum, but the Gauss quadrature should be transformed accordingly. Finally, the double integral is expressed as a double sum. The two-point Gauss-Legendre quadrature for the interval from -1 to +1 is tabulated in the third and fourth columns. The two-point Gauss-Legendre quadrature for the transformed interval from 0 to 2 is found and tabulated in the fifth and sixth columns. For each xi and tj, the function values fij are calculated and tabulated in the seventh column. The last column is the product of the function values and the corresponding weights. Since the weights in both quadratures are all 1, the last column is the same as the seventh column. Summing the values in this column gives the numerical estimate to the inertia moment. The true value of this problem is 48 over 35. The true error of this estimate, denoted as IZ2 by 2, is 2.09 times 10 to the -1. When using three-point Gauss-Legendre quadrature in both integrals, the true error of the estimate is 1.91 times 10 to the -3. When using four-point Gauss-Legendre quadrature, the true error of the estimate is 3.57 times 10 to the -12. This error is due to rounding and should normally be 0. But why should it be 0? I will just put this as an open question for you to think about as I conclude this session. That is all for now. See you next time with another topic. Bye.